Well, hi, everyone. I'm Katie from Hackster. Welcome to Syntiant's Ultra Low Power is Giving IoT a Sharper Edge webinar with Sentient and Edge Impulse. Atul Gupta and David Schwartz are here with us today to share more about how you can use Edge Impulse Studio to create low power, high performance speech, audio, and sensor interfaces using Syntiant's TinyML board. So before we get started, I want to share a little bit more about our speakers today. So we've got Atul. He's Vice President of Analog Design at Sentient Corp. He is an expert in mixed signal microchip and system design with over 12 years of leadership roles. Prior to joining Sentient, he was Vice President of Engineering at High Performance Analog Division of MACOM. He earned his Bachelor of Technology from IIT Kanpur, India, and master's degree from University of Calgary in Canada. David is a user success engineer at Edge Impulse, helping customers build and deploy products powered by machine learning. He is a University of Texas graduate with previous experience in embedded systems design and applications engineering. He lives in Austin, Texas, and enjoys reading, swimming, and programming in his spare time. So a little bit about today's session. We'll have 45 minutes of the webinar will be a presentation and a demo. And then the last 10 to 15 minutes will be open for your questions. So if you have questions during the webinar, there's a little Q&A section at the bottom of your screen. Click on that, type your question in there, and David and Atul will get to as many of those questions as they can before the end of the webinar. And then as an added bonus, Sentient is giving away a TinyML board to 3 participants who attend the presentation and demo with us live today. So winners will receive an email later next week with more information on how to claim that prize. So thanks again for joining us, and I'm going to let Atul take it from here.
Thanks, Katie. You guys can reach me at my email address, atul@sentient.com. In today's presentation, I would be presenting a Sentient solution for ultra low power, which could be used right at the edge, and it can be battery powered, and it could be used for IoT applications, any other applications you can think of. So I would start with the context where you would use this device, what's the issues in the industry. Then I will present what this TinyML solution is all about. Then I'll present like how this stands out from any other solution you might be already using, where this solutions our technology has been used. I'll talk about that. And then I'll pass the presentation to David Schwartz, and he will show machine learning deployment using Edge Impulse Studio. So as we all know, artificial intelligence applications are compute intensive. And that's the reason why most of the applications are running in the cloud. But when you run something in the cloud, people are always worried about privacy because all the data goes to the cloud. Not only that, there is a latency because the signal has to go all the way to cloud and come back. And then what happens if the link is not that reliable, especially when you're using these solutions in the field? So reliability is a concern. To answer these things, Sentient has a solution. We actually have a purpose-built chip which does the AI. And it is really low power. And the reason why it is low power, because this chip is really designed for AI type of workloads. And this AI delivers such a low power that it can be always on devices, and they could be deployed right at the edge. So let me just share the board. This board can be used for pre-production as well as for development vehicle. Earlier on, when people want to deploy a solution like this, they may not want to spend money to develop a hardware. So this board actually comes pretty handy, especially when the volume is less than 1K. And to buy this board, there's really no MOQ, and this is cost optimized board. So you can buy as many as you want, and these are available from DigiKey. Of course, this board can be used for development. You cannot see there is a SD slot on the back side, but with that SD slot, you can actually save 3 days of continuous uncompressed audio data. Or if you're saving the data from a sensor, that could be continuous uncompressed data for 200 days. So this is a great device to capture the data, because AI kind of runs on data. If you really want to reduce the cost, then this board could be used as a guide where you can actually remove some components, change some components, or even add some components. So we provide the schematic and to help you to cost reduce your system. You can follow this link and that will take you to our website. And there are one simple tutorial. We have a written tutorial for Mac and Windows separately. And after the tutorial, you would be able to actually train this chip to understand go and stop keywords. And it takes about 2 hours to complete the tutorial from start to finish, including machine learning and other aspects of it. So this particular board or this particular technology is really based on our neural decision processor. And that takes a very small amount of power. So we're talking about microwatts of power. So for speech and audio application, it takes less than 140 microwatt of power. For sensor applications, the core power is less than 100 microwatt. Some people even ask, is that your standby power or is it something when it is really working? And the answer is that when it is really working, it is doing the inferencing that this power is about. The board is designed as small as possible. As a matter of fact, it can fit in a small electronic gadget, which may be same size or smaller than Apple Watch. So here I'm comparing the size of the board and the size of Apple Watch. So you can see the board is pretty small. And the idea is that you can actually take this board and with the jumper wires, you can enable AI application in your current solution. This is a self-contained board. So it has a PMIC chip, it has a slot for micro SD card. And if you want to drive something and if it doesn't take a lot of power, you can drive it directly. So all you need is a battery, this board, and your actuator, and you can be providing a complete solution. So as I mentioned earlier that privacy is a big concern. And that's the reason we did not put any wireless connectivity on this board, so that people would be assured that data is not leaking through the microwave or other wireless channel. The data goes directly into micro SD card. So it would be in people's control if they want to use or give that data to somebody else or not. However, if your application requires a wireless connectivity, then this expansion port, which you see on the top, could be used to connect it to Wi-Fi modules, BLE modules, and things like that. And these not only provide a signal, but they can also provide the power. So which means that you can actually only power up the module when you really need it, and you can keep it off the other times. This way you would save a lot of power. So let's move on and talk about what's in this board. So of course, this whole board is built around the NDP-101 chip, which is the neural decision processor. It is directly connected to accelerometer and microphone, which means that the rest of the system could be off while NDP chip is working with either of the sensor or microphone. It is provided 0.9 volt and 3.3 volt through LDOs. So when you're first time programming, at that time, you could be using a micro USB connection and the data goes into NOR flash. And every time the system wakes up or it's got booted, then the data goes from NOR flash and then it is populating NDP chip. Once NDP chip gets a model, then the whole system could be put to sleep. And when there is an event occurs, which could be pretty rare, then NDP chip would wake up the host processor, and then host processor could be sending the signal through the header, or it could be showing things on the LEDs. There is a micro SD card which can save the data. So the NDP wakes up the host processor if there is an event happens, and then it sends the data, and that could be stored in micro SD card. This board also has a slot for LiPo battery, which means that the micro, you can charge the LiPo battery through the micro USB connection. And when USB connection is not there, then the whole board is powered with the LiPo battery. There is a 5-volt FET, and earlier, generally you would use a OTG, which is on the go power supply, but here we are actually enabling that, which could be used to power up your accompanying board. And the other signals also go through this header. There is a switch port as well, where you want to actually put a switch which is external to the device, and you can actually solder wires. So which means that switch could be connected on a chassis, and then it could be controlling the operation of the board. So let's talk a little bit more about the details of NDP-101 neural decision processor. So this processor, of course, it has a ARM core M0, but that doesn't do actually neural compute. M0 is mostly used for housekeeping. The neural compute is done with the Sentient Core 1 technology, and that is actually a hardware implementation of neural network, and that actually provides the low power. It has a fully connected neural network. It has as many as 560K parameters. And as I mentioned earlier, that the core power is really low. It's in microwatts. And depending on your use case, it could be 100 or 140 microwatt power. So we have done some benchmarking. To be honest, there is nothing which is even close to this part. So it seems a pretty unfair comparison. But the closest alternative which you can choose, which would be an ARM processor, we show that it is 200 times, it takes 200 times less energy per inference. And then it has about 20 times more throughput. And if you want more throughput, then actually energy per inference also goes up. So the most optimum device which you can find, we show that it has a 1 to 2 order of magnitude more throughput or less power. So this is a link which you can follow to see more details on this study. So now you may be wondering where you would use or where people have used this device. So back in July 28, 2021, we had this press release, and by that time, we actually sold 15 million devices of this technology. Since then, of course, we have shipped a lot more. And these devices have been used in cell phones, earbuds, home security systems, and many more other applications. Of course, we don't want to provide just a box where you would be thinking within the box. In fact, the usage could be many, but just to list few, it could be used for wake-up word or keyword detection. It can be used for acoustic event detection, which David is going to show later in the presentation. If it is tied to your hand, then you can actually use your hand gestures, and it would recognize motions with your hand gesture. There's a huge thing in the industrial application that you want to monitor of machines, and depending on their condition, you do the servicing. So this could be used for condition-based monitoring. And the list kind of goes on and on. And in fact, in this webinar, we're really soliciting your ideas, like how you would want to use it. And we are here to help you. So with that said, I like to pass this presentation to David Schwartz, and he would be talking about using this part and how to program it. So
Thanks, Atul. All right, welcome and hello, everyone. I'm David. I'm a solutions engineer at Edge Impulse. And today, there we go. I'm going to be going over, sorry about that. I'm going to be going over how with Sentient and Edge Impulse, we've made it easier than ever to build and deploy machine learning applications to the edge in the field. I'm first going to give a brief overview of who we are at Edge Impulse, what we do, and why we're so excited to be partnering with Sentient. And then I'd like to give a live demo showing really like a hands-on what it looks like to build a machine learning application on the Sentient TinyML board that I have right here. So to get started, who are we? Edge Impulse is the leading software platform for embedded machine learning. We are an open source and free platform that enables developers, regardless of prior machine learning experience, make use of their data and create powerful ML algorithms that can be easily deployed to a variety of devices. And at the core, what we do is what we like to call data-driven engineering. So to contrast this, the traditional way that you would develop sensor algorithms and embedded products that utilize and process sensor data is with handwritten rules developed over a research and engineering process by a team of domain-specific experts. And this process has seen great success in a variety of applications. You can think things like IR heart rate sensors that have robust traditional algorithms built up around them. But in this new space of expanding IoT and more edged compute and embedded devices, prototyping new sensor algorithms and scaling those sensor algorithms up to millions of devices can become a challenge. So the new paradigm that Edge Impulse enables and that embedded ML in general really enables is this data-driven engineering workflow. In this workflow, rather than have a team of engineers hand design a filter or algorithm to process a specific type of data, we go and we collect data from the context and environments that we want our device to be operating in. That can be very broad, but it can be anything from collecting voice samples in a home to be used for a kind of smart home application. It can be collecting sensor data, telemetry data off of an industrial device to gauge its health and its likeliness to fail in the future. And we can take that data, process it through a learning algorithm, and very quickly get an output algorithm that we can iteratively test, validate, and build over time in order to develop a robust machine learning solution. This is much faster and much more scalable than traditional rules-based engineering in a lot of contexts. And we've already seen that this is taking over in a lot of really exciting new fields. ML-powered solutions are going to drive new value across many industries, from smart home, healthcare, industrial, and other infrastructure products. Things like computer vision, voice recognition, and other sensor fusion, time series sensor processing techniques are going to become more and more popular and more valuable over time. To give some specific examples, this is kind of an overview of the field as we here at Edge Impulse see it, where in predictive maintenance, things such as industrial motors, shipping containers, and other items that can see failures over time or see degradation over time. Whereas before you might go and send out an auditor or technician to check on the health of, say, a fire hydrant every 6 months. With predictive maintenance tools, you can automatically be monitoring and detecting failures early before they happen. In asset tracking, things such as, again, shipping containers or factory floors, we can use ML techniques to come up with novel and low-cost ways to monitor assets. Whereas in the past, you might use a live video feed monitored by a technician or engineer. Now you can use time series sensor data, vibration analysis to decide, okay, is this shipping container in transit or is it stored away, and things like that. So that is bringing a lot of value already. And then, of course, in human interface, I think this is what most people will be very familiar with already. Gesture recognition, voice recognition are all becoming very common, especially on embedded and IoT devices. And that's all powered by embedded ML. So moving on to really why we're so excited about to be working with Sentient in releasing these new dedicated ML processors. This is kind of how we currently see the ML capabilities of various devices. So if you look at the field today, if you want to run low frequency sensor applications such as an accelerometer or current sensing, temperature sensing, you can do that on a very low cost, very low power IoT MCU already. And those are very well suited for those tasks. As you move up in the complexity of the algorithms you're trying to run, however, the power consumption costs as well as the monetary costs of deploying those devices increases. To the point where if you want to do image and video processing, right now you need a higher class of embedded CPU, maybe running an embedded Linux instance, and the power budget and cost of those of that hardware just might not make sense in a lot of environments or in a lot of context. And so what Sentient has done is really just completely raise the bar. The new NDP 101 is, as Atul said, extremely energy efficient compared to even prior generations of low-end MCUs. At the same time, it's incredibly powerful, and it can do high-quality audio processing at a level that previously, with Edge Impulse, we were deploying to much higher classes of processors. So we're really excited to be partnering with Sentient to support their hardware on our platform and allow developers to experiment, as Atul said, with new use cases, new places where these types of ML algorithms can be deployed that just weren't possible before. And so now what I'd like to do is go into our platform and give a kind of live walkthrough of what it looks like to build an ML application with Edge Impulse and with Sentient hardware. As Atul said, we're going to be designing a glass break detection algorithm. We're going to be using, as shown here, we're going to be using some small public data sets as well as some live data that I've collected to design a glass break sort of detection algorithm geared towards a smart home environment. When you're building an application, really no matter where you're starting from, where you want to deploy to, it all starts with your data. And so that's what we're going to go through first. In the Edge Impulse view here, we provide a kind of comprehensive way of viewing, analyzing, and sampling new sensor data. So I've collected around 7 minutes of data here that we're going to use to differentiate between two separate classes. So one is a generic background class. This is, again, geared towards kind of a home office, smart home type of environment. So this includes things like keyboards, doors closing, people talking, and other environmental factors like that. In contrast, we're also going to be providing samples of various glass objects being broken. This is collected from an open source data set. It's been publicly collected, and we've imported this into the Edge Impulse Studio in order to get a lot of samples of various glass objects, from glass bottles to windows being kind of broken. And these are all already sliced nicely into kind of 1 to 2 second windows. However, Edge Impulse fully supports live collecting sensor data off of devices. We have a variety of ways of getting data into our platform, including sensor data off of your development kit. In addition, you can sample from your mobile phone or computer, and we can downsample all of that data into the format and sample frequency that your end device expects. Finally, of course, as I already mentioned, we support pulling in data sets from data from outside data sets, sources, and other database integrations as well. Along with building up a training data set, we also will want to have what we call a test data set. This is very important to collect real world samples that the model won't see during the training process. We're then going to validate the model's performance against this test data. And we're going to use that to benchmark our model's performance as we say, add new training samples later on. Maybe if I'm moving my algorithm from just operating in kind of a home office sort of context to something maybe outdoors or in a factory floor. We want to build up test samples that represent the context and environments where this algorithm will be deployed. And so that's what I've done here already. And once we have this data set built, we can go into our main impulse design tab. In Edge Impulse, this is where you define your complete signal processing and learning algorithm that you want to deploy to the end device. We provide some options around sampling your data in different ways that make sense for different end devices. As I mentioned, kind of downsampling, you can modify the frequency of your data set here. And then we offer a host of DSP preprocessing blocks that we found to be really helpful in terms of extracting useful features efficiently from raw data before sending it into a neural network. With Sentient, we've developed a specific hardware optimized audio block that we'll take a detailed look at in a little bit. But this is going to generate a spectrogram that we're then going to feed into a neural network. So that's the algorithm we've defined here. And I'll hit Save Impulse and then move down to our lower level configurations for that Sentient DSP block, as well as for our neural network. So here we can see the parameters and spectrogram available for the neural network. Let me switch to a sample that's a little bit more interesting. And so up here you can see an example pulled in through our UI of a glass break sample. And then you can see here the output spectrogram image that the Sentient optimized processing block has generated. What we're doing here is essentially creating visual patterns or 2D patterns in this from our raw data. And then we're going to train the neural network to recognize and pick up these patterns that are unique to the signatures of glass being broken. Once I've set this up and everything looks good, I'm kind of seeing that the spectrogram output from a few samples. I want to go through into our platform and generate features. When I do this, this is going to create that spectrogram for every single sample in my data set. And it's also going to give me a visualization showing the relative similarity of the different samples in my data set, colored by the different label or class that they are associated with. And so here you can see there's some interesting groupings appearing that aren't necessarily related to the labels that we're trying to detect. And this is one of those situations where, you know, if you were designing a traditional manually tuned algorithm, it would be very difficult to, it would be very easy to separate whatever groupings these are, but it would be much more difficult to separate on the noise or specific glass break samples that we're looking for that might be clustered closely together. But neural networks are very effective at learning to parse these sorts of similar and related samples. So moving on to that neural network view. Here you can see the UI for designing your neural network architecture. We provide some options around defining your neural network architecture. Here, again, we're using a architecture specifically optimized for the Sentient ML board. And along with this, we're going to be able to configure parameters for how long we want to train, and also options around augmenting our data. Data augmentation is a really powerful tool that lets you, that really helps generalize a neural network against the sorts of data that you expect to encounter in the real world, especially if you're working with a limited data set. As I mentioned earlier, we collected about 7 minutes of data, and that's not much. So in order to kind of help with that limited data set, get the most out of it, we're going to be augmenting it, adding noise and masking out certain time and frequency bands throughout the process of training. And Edge Impulse takes care of all of that automatically for you. From here, you'll just start training, which I've already run for the sake of time. But once training is complete, you'll get a comprehensive look at the accuracy and performance of your model, showing you the per class accuracy, as well as the same feature explorer view with now showing the labeled results. So we can get an idea of where our neural network may have struggled to accurately classify data. And this is the sort of intuition that is really great when building up additional training and test data. When you see samples clustering over here, Edge Impulse lets you manually open and investigate these samples so you can get a better idea of what is causing issues in your data set. So here, this sample looks like this glass break sample is kind of near the end of the window. So we kind of have an empty window here. That's something that, through further iterations of our data set, we might want to clean out or process. And that's really the power of this kind of feature explorer view. Once we've designed our neural network, the next thing we need to do is test it. So as I mentioned, in our model testing view, we can go through and classify our entire data set, our entire testing data set, and benchmark our model's performance against it. This will run in the background. And while this is running, I'll just chat a little bit more about the advantages of using Edge Impulse to kind of deploy these sorts of models quickly. So everything you've seen here in the API in the UI can also be API driven. So whereas I'm going through manually clicking through our UI, defining the algorithm, kind of going through maybe tweaking the number of training cycles, all of that can be automated. And so what you're able to do is, as you get your pipelines for collecting data, processing that data, and then experimenting with new algorithms and test sets, that can all be automated and integrated with existing CI and CD workflows. So that's a really powerful tool for, again, just building up that model's robustness and capability over time. So now that testing's done, we can see that actually the testing accuracy is a little bit better than the training accuracy. This is generally a good sign. It indicates that our model at least is properly recognizing real features that are relatable to our test data sets, glass break and background noises. But it also might be an indication that our test data set is a little bit limited, that we might be, again, if I'm just operating in my home office and my test data reflects that, it might be a sign that, hey, if we're going to be deploying this to different environments, we need to kind of make sure we're covering all of the different contexts that this device will be running in. But for now, just for the sake of the demo, this is a great result. It shows that the model's at least training to real features and not overfitting just to our training data set. Along with that process I was talking about earlier, of iterative kind of collecting more data, retraining your algorithms, and then retesting it, Edge Impulse also supports versioning, taking snapshots of the entire data set and algorithm of your project. You can save these over time and restore back to them at any point. And this is really useful for, again, as you're benchmarking performance, if you add data that causes issues, or if you need to trace back kind of where a certain behavior came from, you can do that with our versioning tool. But for now, I'm just going to skip straight to deployment, where we're going to look at the options for actually deploying this algorithm that we've trained and developed to a real device. So generally at Edge Impulse, we provide kind of a standalone and portable C++ library for all of our models. This can be deployed on a variety of tool chains, and with vendors like Sentient, who we've partnered with, we will implement very hardware optimized implementations of our algorithms in this library. So we have this dedicated Sentient library output here that you can deploy to. And you can use this too if you're building a custom application with the Sentient board. You can take this Edge Impulse output and then essentially just call into a single function to get your results back. And then once you have those results, you can process them in your application logic. However, for the sake of demoing, we also offer a zero code pre-built example firmware for the Sentient TinyML board. This is the fastest way to go from the data collection tab that I showed earlier all the way down to getting this running on a device. And it's what we're going to be using here. When we build this, a unique feature of the Sentient TinyML board is the ability to configure different parameters around when we consider a neural network result a valid detection. This is important in terms of interpreting, say, what does it mean if I see a 70% or 0.7% chance that that a glass break has been detected? When do I decide that that threshold is suitable to activate whatever business logic and whatever my application needs to do? And so Sentient offers for voice applications some data sets around calibrating against a long sequence of human voice over the radio. And you can also upload your own for kind of custom applications. Here, we've just manually tuned these posterior parameters based on some empirical testing that I've been running. But this is a really powerful tool for, again, building up kind of even more kind of context-aware and context-specific performance out of your model and out of your Sentient TinyML board. So once we've decided on this, we're going to build the application. And this is going to run for a little bit while it compiles my model, compiles the firmware, and at the end, it's going to let me download it. So in the meantime, I've gone ahead and already flashed a board here, just so we can test this out. So let me show my terminal real quick. Hopefully you can see that. And so what we're going to do is, so what this demo firmware does is it can run any model that you design that samples from the microphone or other supported sensors. It's then going to run all of the processing, all of the deployed neural network that we trained in Edge Impulse on the NDP 101. And it's going to utilize that really low current consumption that the NDP offers to kind of continuously sample the environment, determine if interesting events are occurring. And then if an interesting event, specifically here, if a glass break event occurs, it's going to turn on an LED. Simultaneously, it's going to be outputting the results of the inferencing that's going on, that continuous listening, to the terminal, which we can view here. So in order to test this, what I'd like to do, I don't want to break any glass bottles over my desk, but I'm going to go through and play a few samples from my testing data set and use that to kind of show it running on the device. And so you can kind of see it here. It's already, kind of continuously listening to my voice. And once I start running this, you'll see kind of the output from the terminal. And then what I'll do next is I'll go through and we will play a couple samples. So I have a few prepared here. First, I'll play a few glass break samples, just so you can hear or see how it responds. There, the LED lights up. Play a couple more. There it goes. And so this is all running on device. And it's consuming very little power while doing so, which is really cool. And then what I'll next show is a few samples of just background noise, non-voice, just to give you an idea of what this is, of what it's picking up and what it's basing its inferencing on. So first, I've got a couple samples I want to show here. Hopefully this one isn't too loud. It's kind of just loud noise. Just showing we're actually learning to detect the signature of glass breaking. And then I've also got kind of an alarm. And so what I really encourage and will hope everyone gets out of this is this project, along with kind of the TinyML board, is available. The project is public, and you'll get the link after our presentation in the slide deck. And so I really encourage everyone to really try this out for themselves. Use this data set and this project as a starting point to either modify this existing data set, take it and build on it. Build out, a glass break detector for your environment or wherever you're interested in deploying it, or build a completely unique project. It'll all run with the Sentient ML Edge Impulse firmware. And so you can really rapidly prototype ML applications and take advantage of all of the industry-leading features that the Sentient TinyML board offers. So that's about it. That's all I want to cover in my demo. So let me go back to my slides really quick. Here's links to all of the resources. Of course, the slide deck with the actual clickable links will be forwarded after the presentation. Let's now jump into a Q&A, and if there's anything we don't get to in the process of that, feel free to reach out to me directly at david@edgeimpulse.com. I'm happy to answer any questions or help you build your ML applications with Edge Impulse. Thanks.
Great, thank you. Atul's answered a lot of these questions already, but we might go through and try to answer some of them live too, so that we have we can make sure you all see those. But one of the questions that we have right now is, what is the latency of each inference?
Yeah, I was just about to write that one. So the way it works is that we ingest the data and then we do the processing and then we ingest the data again. So pretty much you can see that the latency would not be more than between 2 frames, which is generally is at 10 millisecond, 25 millisecond, things like that. And for all the purposes, this is pretty much instantaneous processing time. Okay.
Great. Okay, we actually had a couple of questions about the Linux development. Do you have a plan for that for the future?
Okay, so we provided Mac and Windows because we are expecting that people who don't have any background, they're not really coming from engineering background. And these tutorials are actually for those people. For Linux people who are using Linux, we expect that they are already kind of a proficient user and they understand these things. So once you look the presentation and you go through the presentation through either Mac or Windows, after that, you'll be pretty much trained, and there's nothing which prevents it to work on the Linux environment. It's just that we did not actually provide a specific tutorial because we expect those people would already kind of know what they're doing.
Okay. Does it support deep sleep mode and interrupt using a wake word?
Sorry, let me read the question again. Let's support deep sleep mode and interrupt using wake word. Yeah, so the chip itself is always working. So the chip never actually, the NDP chip never goes into deep sleep because this is always working. And yes, your host processor is supposed to go in deep sleep mode. And then when we find a relevant or a classifier which is representing, then it would actually wake up the host processor. So I hope that kind of answers the question.
Great. We have a question from Brendan. Is there any difference in approach on data from one sensor versus multiple sensors? He has a use case where you have 3 or 4 time of flight sensors arranged to detect pedestrian traffic through a door or gate.
Yeah. So this current board actually is designed with only one sensor. Now, if your application actually is looking for multiple sensors, and if the data coming out from these sensors is also expected to be correlated to each other, which means that you want to actually get the information from multiple sensors, which is also known as a sensor fusion, then it's a little bit of work is required, and we can guide you if you are very much interested. But that's not something which is available in a more streamlined fashion. And the main reason is that the complexity or the definition of that really varies because you would have 2 sensors, 3 sensors. They may have multiple axes of data coming through. Their sampling rate may be different, and it is not easy to actually construct one tensor. So that I would say that is really expert level kind of usage. And you can reach us and then we can guide you how to do that. And we'll be very happy actually, because that's where the true AI kind of comes to fruition. So please reach out to us on that one.
Great. And I'll share the email, your email in the chat in a second too, so you guys have that. Okay, great. So here's another one from Albert. Great feature to provide a clickable neural network design. Is it also possible to define your own neural network, Keras, in a terminal?
Yeah. So this is our Sentient Core 1 technology, and that actually has a fixed neural network. And the reason why we use that one just for the simplicity. Now, our next generation chips are a lot more capable, and you have to reach out to us, and we can actually guide you depending on your application. But yes, we have other generations of products where you can actually define your own neural network.
Yeah, exactly. And I'll just add that within Edge Impulse, you absolutely can go straight into Keras and kind of work through whatever you want to do. And so just to even if you're using kind of the Sentient neural network architecture, you can define your own custom data augmentation via our Keras block. So yeah, that's all completely customizable in source code.
Great, thank you. Any plans to make a chip for image processing?
Yes, so if I'm not mistaken, I think we have some press releases. So please go on our website and look for it. Image processing is definitely a great market for us. This particular board is not designed for that, but in future you could expect image processing devices as well from us, and complete solution for that matter.
Okay, great. And I'll send a link to the news on Syntiant here in 1 second. Here's a question from Manuel. Are the schematics or design guides for PCB available?
Yes, so schematic is on our website, which I think there is a link, and you go on that link and you would actually see on our website, there would be a schematic. The layout is not, there's nothing very specific in the layout. So you can do your own layout. That part we have not provided, but it should not be a big deal because there are only a few pins, and most of these pins are actually low speed pins to begin with.
Okay, great. And just typing the link for where you can find the schematic too in the chat. So awesome. Can you discuss how students who have taken an undergraduate DSP course can use this board in conjunction with Edge Impulse to learn machine learning?
Yes. So this is really got me going because we are talking about democratization. And when we talk about democratization, which means that we have to consider both the people who are new to the field and the people who are expert in the field. And this board actually could cater to both of them. And the tutorials which we wrote are actually targeting people who may not know anything about neural network, who may not know anything about AI. And we have tried high school students to actually complete the tutorial. So on one side, we are actually catering the people who are totally new. On the other side, we have engaged with the professors, and even PhD students can find it very interesting. So yes, there is a whole, there is a continuum of people who can make use of this thing and then try out their learning into that one. So yeah, please reach out to us. This board actually is considered as an educational board as well. And we would be very happy to actually talk to your professors, etc., and then make it even a part of your curriculum. But, and if you find it interesting, we definitely are going to help you there.
Great. Okay, question from Andreas. How long does it take to be ready for processing after power on? Reason, even if the chip uses microwatts, is it too much for us to run it the whole time?
Okay, so once you boot the chip from power down mode, it takes, I think, about 5 to 10 seconds because the model has to go from the flash all the way to NDP chip. And during that time, it could be powered up from the micro USB because you may be actually powering it up in the, let's say, your factory. And then you can actually take the whole thing and you can deploy it. And it goes into sleep mode just after that. So then it is start. So once it is already programmed, you can remove it from the micro USB and it would be already in the low power mode. And let me know if that solves your concern or not.
Okay. From Naveen, what kinds of network models are supported out of the box? Can I use RNN?
Yeah, so there, as I said, that this particular board is really limited to fully connected neural network. And for anything more exotic, we have to actually look into the second generation, which is Sentient Core 2, which is also available, but not in this particular form factor. And we would be actually making it available soon. But we have found that most of the applications, the amount of neural network we are providing is more than sufficient. And probably Dave can actually attest to that, with very small amount of data, it's quite easy to train. So we have not come across to a problem which could not be solved in this TinyML kind of background. But yeah, I would say that give it a try, and giving it a try is pretty much easy on the Edge Impulse website. And if it doesn't work, then let us know, and we'll definitely give you the right solution for it.
Great. So those are all our open questions. If you do have questions, go ahead and post them yet, but we'll go back to some of the other ones. I think there were a couple that I saw that I wanted to.
And the one which I have provided a written solution, maybe I can talk
yeah,
about.
I was just going to go grab one of those. If you have one that you wanted to bring up yourself, go ahead and let me know. Otherwise, I was going to go.
No, I think just go through the list.
Okay, great. So this one I thought was good. What Wi-Fi module would you recommend for this board to keep low power consumption?
Yeah, so as I said that the best way to save power is not to power up the Wi-Fi module at all during the always on mode, because most of these deployments happen in the field where that particular incidence is really not happening. And sometimes it may be days before a particular event happens, which you're detecting. So if you power up your, let's say, Wi-Fi module or any other module, and even if you keep it in a standby mode, it still might be taking microamps of current and eventually drain your battery. What I'm recommending here is that you can actually cut its power supply. And if it has the right amount of power supply, our board can directly provide it. When the event happens, it would actually boot up the Wi-Fi module. So yes, there would be some latency, but if something is not happening in several days, I would expect that the latency at that time of a few seconds would not matter. And then you would power up the Wi-Fi module, and then that would actually send the distress signal. So I believe that would be the lowest power solution, but it really depends your latency and actual Wi-Fi module which you have chosen. And we definitely would be happy to work with you and give us our recommendation. As I mentioned in my answers, that Arduino Maker Series actually is pretty convenient, because on the same platform, they actually have a different type of wireless solution, BLE, NB-IoT, Wi-Fi. So you can give that a try first, and we'll be able to help.
Great. One from Timothy came in. Can I use it for vision AI-based applications? If yes, which camera module is compatible?
Okay. So again, this particular board was not intended for image application, and the image applications should be coming in next generation ICs. The image which is used here is 40 by 40 pixels, which may be not sufficient for most image processing needs. So I would just say that reach out to us and we'll provide a different solution. This particular board was really not intended for image processing.
Okay. Let's see. How many words does the Sentient chip can detect simultaneously?
Yeah. So the maximum limit which we have is 64, because we have 64 classifiers on the output layer. Now, depending on your choices of the words and the accuracy you're expecting, the practical solutions which we have seen is using as many as 10 words. And also how you want to use these 10 words. For example, if you say, Alexa, play music, and Alexa, stop music. So you can say that Alexa and music, they are the same. So there are really 4 unique words in this one, even though there are 2 phrases. So it's not that we actually have to tell it or train it with the 6 words. It's actually 4 words. And then you can actually make a more complex, let's say, a phrase, just like Alexa play music. Not only that it's easy to use, but from the robustness point of view, it is also good because three things have to happen for it to wake up, which means that reliability and the false acceptance ratio would also be less. So it's you can actually provide a very good solution by actually choosing more words. And again, reach out to us, both Edge Impulse and us, and we can actually provide you a solution.
Great. Is the 100 microwatt the power consumption of the Sentient IC or the module with M0 plus processor?
Yeah, so that particular power actually is for the chip, and the whole system actually takes more power because there is a microphone connected and there is still a residual current taken by the processor. And again, we could have used more DC to DC converters, but then there is a trade-off with the cost. So we tried to do optimization there. But if you have a requirement where the power has to be like extremely low, then we can help you there and provide you better solution.
Great. From Manuel, is it possible to train the IMU to infer from movement the force exerted?
Yes, of course. That's the purpose of IMUs, that you provide a force onto the device, it moves, and that is get registered in IMU. And then you can use that information to do the recognition of those gestures or forces. The answer is yes.
Okay. The board datasheet talks about the possibility of using the board to detect voice and audio signals and to detect movements. Can other types of external sensors be connected? Can I use signals from different sensors at the same time as an input to a neural network, not only movement or sound at one time?
Yeah. So as I said that the board is designed where NDP signals are connected to these two sensors, and those particular connections are not brought out from the board, which means that you won't be able to connect the other sensors on those nodes. There is an expansion port where you can actually connect it, but at that time the data has to go from the external sensor to the host processor, and then host processor would pass that data to NDP chip, and then you can actually do the inferences. So this particular solution is not really like, the power would still be higher because host processor has to be up and running, but you can get the job done. So depending on your need, let us know. And again, we would actually consider this feedback for our next generation boards as well, where you can actually connect to multiple sensors.
Great. Are the features just the row spectrogram data?
So for audio application, the features, you generate an spectrogram and then you feed into neural network. That is the standard way of doing it. And that's how we do it as well. But if you are using, let's say, with a sensor, then in some of the applications which I have seen, there is really no need to convert another engineered layer of signal. So you can actually feed data directly and then it does the job. And if you find that your application really requires some kind of other type of vectors, then we would be able to guide you there.
All right, great. Well, it looks like we are up on our hour and we've answered all our questions. Oh, one more. Can we do one more?
Yeah, sure.
One last question and then we'll call it. All right, so from Manuel, back to the IMU question. I'm interested to classify the force to detect levels, or I'm interested to classify the force to detect levels, not just movements. For instance, to detect if a given movement was faster than another.
Yeah, I think that's, if you can measure through IMU, and if there is a measurable signal and that goes into neural network, then you should be able to classify it. So answer is yes. Of course, we have to give it a try and then see if there's an issue or not. So reach out to us and we definitely would give you a solution.
All right, great. Thank you so much for the presentation, for your demo, David. We appreciate it. Thank you everyone for joining us today, and we will see you the next time.
Okay, thanks a lot. Thanks, Katie.
Bye.
Thanks, David. Bye.